So we have been continuing, our discussion on network growth model, and last lecture we have discussed, why network growth model is important, right? Why synthetic network generation is important, and we also have discussed a simple model called random graph model, okay, ER model, erdos-renyi model, and in the ER model we have seen that the three properties that we want to satisfy. One is the high clustering coefficient, high local clustering coefficient. The second one is scale free property, and the third one is small world property. These three properties need to be satisfied, but in case of ER model, we observed that except small world property, the other two properties are not satisfied, right? High local clustering coefficient is not satisfied. We have seen we have seen the last lecture that with the increase of the number of nodes, right, the clustering coefficient will decrease, right? But that should not happen, because in the real world network we observed that large networks with millions of nodes, the clustering coefficient is still quite high, 0.4, 0.5 around, right? And obviously the degree distribution follows Poisson distribution or binomial distribution in case of ER model, which is not the same as the real world model, which actually follows power law degree distribution. So these two properties are not satisfied by the ER model, okay? And therefore, if you look at the statistics, right? Let's look at the statistics and let's try to understand that the last lecture we mentioned that the path length, right? The average path length, which actually indicates the small world behavior, it proportional to the logarithmic of the number of nodes, right? It is basically log n by log d or log k, so which is the average degree, right? So if you fix the denominator, it basically scales with log n. So let's see whether this approximation of the average path length actually is same as the average path length that we generally see in case of real world networks, right? So if you look at the statistics here, right, there are several real world networks here, and you see the number of nodes, number of edges, right, average degree, average path length, maximum path. This is the diameter of the network, and this is log n by log k. So we basically want to see whether the average path length, whether it is approximating this one, whether this quantity actually approximates the average path length. Okay, so this is the last row indicates the approximation that we can actually measure. You see that the numbers are quite same, 6.98, 6.58 in case of internet network, in case of World Wide Web 11.27, 8.31, in case of say mobile phone 11.72, 11.42. For some networks, yes, these are not exactly same. For example, this one or this one, right? But if you look at in general, right, they are more or less same. Okay, so this is the average path length that you can observe, right, in a real world network, and this is the approximation that you can actually observe, right? So we see that this is more or less, I mean, this quantity is more or less same as this fraction. Okay, but nevertheless, I mean, the final observation is that this ER model, random growth model, is not enough because of the non-scale free property and the clustering coefficient, which is basically quite low. So in order to address this problem, these two problems, so later on different other models had been proposed, and one such model was the regular ring lattice network model. Okay, the ring lattice network model is a very simple network model that we can think of. I mean, generally no one will believe that this model actually mimics the way real world network grows over time, but at least this is a model by which you can show that the clustering coefficient would be high if you follow the ring lattice network growth model. Okay, so let's try to understand what's this ring lattice model. Okay, and this is regular graph, meaning that nodes have same degree. Okay, so first let's fix the degree of a node in this network. So let's fix the degree as k. Okay, so each node has degree k. Okay, in this particular example, k equals to 4. So this is actually a 4 regular ring lattice network. And how this lattice structure is basically constructed? So for every node, is connected to k by 2 nodes in the left side of it and k by 2 nodes in the right side of it. Okay, meaning that if you linearize this structure, okay, it basically would look like this. Okay, so say for this particular node, if k equals to 4, it means that it is connected to 2 nodes in the right side and 2 nodes in the left side. So this is one such connection, this is another such connection. Okay, and this is one such connection, this is another such connection. In this way, similarly for this node, it is connected to this node already, so will also be connected to this node, these and these. Okay, and so on and so forth. So this example is for k equals to 4. Okay, so if this is the structure, what would be the local clustering coefficient of a node? Okay, let's try to understand it first. Let's think about it. Okay, let me draw a graph first. Let me draw a graph. So let me linearize the lattice structure. Okay, so you will have like this. Okay, and let's say, okay, let's only focus on a particular node called V. All right, so degree is k, therefore V is connected to k by 2 nodes in this side and k by 2 nodes in this side. Okay, so let's say the last node, okay, the k by 2th node in the left side. So this is left, this is right, k by 2th node in the left side is V1, this is V2, and similarly in the first node in the right side is V3, and so on and so forth. Okay, and how these connections are actually happening? So basically it is connected to this one, it is connected like this. Okay, like this. Right, and we are interested in looking at the number of edges, right, number of edges among the neighbors of V, and that's the local clustering coefficient among the neighbors of V. So we are interested in understanding or measuring the number of nodes among these nodes. This is the clustering coefficient. We take the induced subgraph and then we measure the number of edges, not number of nodes, number of edges induced, number of edges in the graph induced by the neighbors. Okay, so now let's think of the number of edges. Okay, remember that V1 is also connected to this edge. Sorry, not this one. So it is already connected to V2. It will be connected to this one, this one, this one, and so on. So V1 is also connected to k by 2 nodes in the right side. Okay, and all those edges which are actually connected to V1 in the right side of V1 will be counted while calculating the local clustering coefficient of node V. Pause and ponder and think why it is so. Okay, so how many edges we need to consider for node V1? How many edges which are associated to V1 will be considered in this calculation? Okay, so we need to consider we need to consider k by 2 minus 1 edges. Why k by 2 minus 1? Because V1 is connected to k by 2 number of nodes in the right side of it, right? Why minus 1? Because V1 is also connected to V. V1 is also connected to V, but that edge will not be considered while calculating the clustering coefficient. Therefore, k by 2 minus 1. Similarly for V2, okay, V2 is connected to k by 2 number of nodes in the right side. So this node, this node, this node, right? But we will not consider the connection which actually which actually connect V2 and V. So again k by 2 minus 1, k by 2 minus 1, right? And so on and so forth. So so for each of the left side nodes of V, we will add k by 2 minus 1 number of edges. So dot k by 2 minus 1, and how many times? K by 2 times. Okay, right? So what's the total number of edges? So this is k by 2 into k by 2 minus 1. Now this calculation is done with respect to the left side of V, right? Remember one thing, we have already considered edges like this, right? For example, the immediate left side of V, right, for which we have also considered k by 2 minus 1. Therefore, it means that we have already considered these edges, right? Why I am saying so? Because when I look at the right side of V and look at how many edges we should consider, we should not consider these edges because this has already been considered. Okay, so this number of edges are basically considered with respect to the left part of V. What about the right part? So let's look at V3. V3 is the immediate right neighbor of V. Okay, so if you think carefully, V3 is also connected to k by 2 nodes in the left side of it, and all these k by 2 nodes have already been considered before while calculating this part. So only V3's right part will be considered. Okay, so how many edges we will consider for V3? So V3 is also connected to k by 2 nodes in the right side, right? But remember, V3's last node in the right side, would be somewhere here, which is not part of V's neighbor, because V3 is located in the first position of the right side of V, right? And V3 has k by 2 number of edges in the right side. So this edge will also be connected to V3, but this edge will not be considered while calculating the local clustering coefficient of V, because this node is not a part of the neighbors of V, right? So how many edges will be considered in that case? K by 2 minus 1 for V3. What about V4? Same calculation, k by 2 minus 2, right? K by 2 minus 2, and think of the last node. Right? Or second last node, not the last node, second last node. Okay? In case of second last node, only one edge will be considered, this one. So dot 1. Okay? So, and this is the series, and we know that how to calculate it. Basically, this is k by 2 into k by 2 minus 1 by 2. This is the sum. So the total number of edges among the neighbors of V is this number 1 plus number 2, number 1 plus number 2. So if we take the sum, this is going to be 3 by 2 k by 2 minus 1 by k by 2 k minus 1. You do the calculation, you will get this number. Okay. This and this will cancel out, so we will basically have 3 k minus 2 by 4 k minus 1. Okay. So if you take the sum of 1 plus 2, and if you also need to divide, sorry, I just forgot to mention, you also need to divide it by the total number of the total number of possible edges between total number of possible edges among the k neighbors, right? That is k into k minus 1 by 2. So if we take the sum of 1 plus 2 and you divide it by k into k minus 1 by 2, that's the clustering coefficient of V, right? And you will get this number, 3 k minus 2 by 4 into k minus 1. Okay, so which is in the asymptotic label, this is 3 by 4, proportional to 3 by 4. So what does it indicate? It basically indicates that the clustering coefficient of a node, local clustering coefficient of a node in a regular lattice network is always 3 by 4. As the network grows, let the number of node increase, doesn't matter, the clustering coefficient will always remain same, 3 by 4, right, which is quite large. So the clustering coefficient property that a synthetic model needs to satisfy, okay, so it is being satisfied by the regular lattice model. But the problem is, there are multiple problems. The first problem is the small world property will not be preserved, right, because the average path length would be quite high. It's a regular graph, each node is connected to only the neighbors, so if you really want to jump from one node to another node, it would not be 6 degrees, for example, right. So average path length would not be logarithm of L. So that's the property which is not followed by the regular lattice. Okay, and obviously the other property is the power law degree distribution, which will not be preserved at all, because this is ultimately a regular graph. So nodes will have same degree, therefore the degree would be uniform, right? Degree will be same. But nevertheless, at least we understood that in the regular lattice kind of formulation of a graph, the clustering coefficient can be preserved, whereas the ER model, random graph model, the small world property, right, will be preserved. So let us try to come up with a model which in one spectrum behaves like a small world, like a regular lattice, and another spectrum behaves like a random graph. Okay, if you think of a spectrum, right, one spectrum, in one side of it, one extreme side of it, you will have a regular lattice, and you keep on changing, and then you will get a random network, right. So the other extreme will preserve the random network property, this extreme will preserve the regular lattice property, and in between these two we will have, we may find some sort of small world property, okay, or say scale free property. Okay, so let's try to understand this. So Watts-strogatz, right? This is called Watts-strogatz model. Watts-strogatz model actually, combines the idea of regular lattice and random graph models. Okay. So what is their suggestion? So their suggestion is as follows. They are saying that let's start with a regular lattice. Okay. Let's start with a regular lattice structure, and then what you do, you basically choose a node, okay, and one of its edges. Okay, the node is connected to k other nodes in the graph. Let's choose one of the edges, and let's try to rewire it. Okay, meaning that let's try to connect that edge to another node. And how do you connect it? With certain probability, with certain probability beta, right, you basically rewire it with another node with which the given node has not been connected. Okay, meaning that let's say this node 13, okay, you take one of its edges. For example, you take this edge, right, and let's okay, forget about this. Let's think of this edge. Okay, this edge 13 to 15. Okay, so you choose this edge and then you rewire it. How do you rewire it? You open the connection, right? You choose I mean one of the remaining nodes present in the graph, right, again uniformly at random, and then you connect it. For example, you choose node 1 and then you connect 13 with 1, okay, with certain probability beta. Okay, and this beta is same as the probability p that we mentioned in case of ER model. Okay, so as you keep on rewiring things, the regular lattice structure will break, and as you keep doing, you actually tend to move towards more random network kind of structure, because you are breaking the regular structure, regular graph structure, and you are making this thing random. You are making the connections random. Okay, so if these kind of things happen, then what would be the clustering coefficient? What would be the change of small Bohr property, and so on and so forth? Let's try to understand it. Okay, so as beta tends to 0, meaning the rewiring probability is 0, it would basically follow a regular lattice structure because there is no rewiring case. And if beta tends to 1, then it becomes more and more random. Okay, so there are two spectrum, right? So there are two spectrums of it. So in one spectrum you will see that there is a regular lattice structure like this, okay, when beta equals to 0. When beta equals to 1, you will have, right, you may have a random network like this, same number of edges. But remember one thing, when we rewire, we will avoid two things. We will avoid the case of self loop, and we will avoid the case of parallel edge, right? It would not happen that you connect this with itself. It would not happen. It will also not happen that you connect, you basically connect it. So okay, it will not happen that this kind of self loop structure will form, or it will not happen that parallel edges will be formed. Okay, so let's try to understand what happens in between these two. Beta equals to 0, say beta equals to 0.01, what will happen, how the graph looks like. Okay, we will analyze this thing now. So this is the empirical results. Okay, let's try to understand this curve. This is a very important curve. So the x-axis is the rewiring probability, beta or p, whatever, right? And the y-axis corresponds to two things. You see here there are two quantities that we are plotting. One quantity is the clustering coefficient, this one, and the other quantity is the average path length. Okay, so what we try to understand is that what is the clustering coefficient. Let's look at this curve first. Okay, what is the clustering coefficient of a node at this point when p equals to 0 or beta equals to 0, and how this clustering coefficient will vary, and what would be the clustering coefficient when p equals to 1, beta equals to 1, how the clustering coefficient will change, right? And what exact quantity we are plotting here? We are plotting a ratio, which is the ratio of the clustering coefficient of the network at a certain value of p and the clustering coefficient when p equals to 0, because when p equals to 0, we know that what's the clustering coefficient. When p equals to 0, meaning that there is no rewiring, right? P equals to 0 means you have a lattice structure, and we know the clustering coefficient is 3/4. Okay, so at this position, C p equals to 0 is 3/4, right? And as you change p, as you increase p, Cp value will change, and we measure this ratio, and we'll see whether this ratio increases or decreases. Now think about it. As you increase p, you are adding more randomness. Okay, you are adding more randomness. So what would happen? The clustering coefficient will decrease, because you are now randomly you are doing random rewirings. So the connections among your neighbors will decrease. So the clustering coefficient will decrease. So the numerator will decrease, denominator will remain same. The numerator will decrease, so therefore the ratio will also decrease. As you see here, the ratio is decreasing with the increasing p. Okay, if p is 1, meaning the network is completely random, we know that the clustering coefficient will be very, very less, right? Because in the earlier in the model we have seen that the clustering coefficient is inversely proportional to 1/n, and of course although here n is fixed, but when you make this thing completely random, there is no clustering coefficient at all. Okay, so this is the change of the clustering coefficient. Okay, now let's look at the change of the average path length. And if you do this, so, and remember this is a simulation results, meaning that you have certain you start with a regular lattice, and you keep on changing, and you keep on getting different networks, and you are basically measuring these things. So this is empirical results, simulation results. Okay, and we are trying to explain the simulation result here. So average path length behaves like this. What does it mean? Let's look at the average path length at p equals to 0. So let's assume that you have certain average path length, right? So as you increase p, what you are doing, you are basically letting a node connect with a node which is far from the given node. Because currently in the regular lattice structure, a node is connected to only, the node is connected to its immediate right side neighbor, or the second up neighbor, or so on, immediate right side, immediate left side neighbor. So as you increase p, you are actually letting the node connect with the other nodes which are far from the given node, right? So obviously the average path length will also decrease. Think why. Okay, so the average path length will also decrease. Therefore this ratio will also decrease. So you see a decreasing curve like this. Okay, both the curves are decreasing, but the way these two curves are decreasing, these two quantities are decreasing, they are different, right? So clustering coefficient is decreasing slowly, whereas the average path length is decreasing suddenly. So in this region, you will see that, say in this region of p, right, if we focus on this part, okay, or say if you just focus on not this part, let's focus on slightly left part of it. Let's focus on this part, for example. Okay, what you will see in this particular region, you will see that the clustering coefficient is quite high, and the average path length is also quite less. Okay, the average path length is quite less. It basically says that, so this part, when p equals to 0, this indicates a regular lattice. When p equals to 1 indicates the random graph, right? But this part is something which follows two properties of a real network. high average clustering coefficient and low average path length. So possibly this part follows the small ball property. Okay, so this was the proposition of Watts-strogatz. So you can actually generate a spectrum of graphs using Watts-strogatz method by varying, varying the size of, by varying the values of p. Okay, so that is okay, but what about the this power law degree distributions? Scale field property is not preserved till now. So we have understood how to generate a network with high clustering coefficient. We have understood how to generate a network with low average path length, right? But we don't know how to make this thing. I mean how to make a network which would eventually follow the power law degree distribution. So in the next lecture, we will discuss one such model, which is called a Barabasi-Albert model, which is the first model that allows a network follow the power law degree distribution. Okay, so we stop here today. Thanks.